Okay, hello and welcome back. In this video, we are covering 2.7 linear inequalities in one variable. So we've been working with equations um, for these first couple weeks, and a lot of the skills for solving equations apply directly to solving inequalities. So we'll define what those are and see some examples. So a linear inequality, and we'll also discuss um, interval notation and set notation. A linear inequality, and we're still in one variable, looks something like ax plus b. We would read this is less than c. This next one would read ax plus b is less than or equal to c. Ax plus b is greater than c, or ax plus b is greater than or equal to c, where a, b, and c are just some numbers. So you can imagine we've been working with equal signs here. So it's a different kind of statement. Instead of saying something is equal to another expression, we're saying the expressions have some kind of relationship using these signs. So you'll see, if you're not familiar with these, we'll just quickly define what they are. And should actually leave some space. Let's just do one at a time. So this one would read is less than. And you read it from left and right. So this would be some statement. We would say is less than the other statement. The arrow or this like opening always opens up towards the greater side. So this would be whatever is here is less than whatever is over here. And then if you see something, you can see the same symbol but with a line underneath. This means less than or equal to. So meaning it is either less than or it's equal to the statement on the right. So notice these will produce like many possible solutions as opposed to just one equality. This thing has to be equal to this. And then if we flip it around, then this would read greater than. And then similarly, this would be greater than or equal to. So let's look at a couple examples, and we'll also introduce um, the notation for describing a whole set of solutions as opposed to just a single solution. And I think we saw a little bit of set notation um, at the start of the course. So we'll reintroduce that and continue using it. So let's look at this example. It wants us to graph each inequality and express the solution in set notation and interval notation. So the first one is reading x is less than or equal to 2. So let's try to graph this. And when we say graph, we just mean we're thinking of a number line. So these would be all the all the real numbers, and you want to visually express some interval of values. So if this is 0, then we would have positive 2 over here. And we want to include everything that is less than or equal to 2 in our solution. So there's two different ways we can write this. We can either, well, we definitely want to include everything less than 2. So you can imagine like shading the left side of this. And in terms of, we have to describe if we're including 2 or not including 2. And in this case, we are because it's less than or equal to. So we can either show this by including a filled in circle, at 2. Another way you can do it is to put a bracket to show that we're including it. Generally, in interval notation, you use a bracket if you're including an endpoint. So we'll see that. I think in the homework questions, when they have you graph this, it's this like bracket or parentheses form. You would use a parentheses if you're not including the endpoint. If this was strictly just less than 2 and didn't have this little equal to sign, you'd use a curved bracket. And we'll see that in the interval notation as well. So I'm going to use this bracket notation just because I think that's how the homework questions are going to set, um, like, that's what they would show as your options in terms of submitting your result. But it could also be represented as a filled in dot or an open dot if it was not equal to. So that would be the graph form. And then let's put it in set notation and then also interval notation. So set notation, if you recall, towards the beginning, we built solution sets and placed our solution inside. So it's a similar thing here, but now we need to describe more than one value. We need to describe a whole interval of values. Really, we're trying to say everything, every possible real number less than or equal to 2. So it's an infinite number of things that could be a solution here. So if you remember, set notation uses curly brackets. So I would open up a set and I'm going to say all values x such that x is less than or equal to 2. So just to explain, this vertical line means such that, which just means we're about to define what this x is. So all values of x such that x is less than or equal to 2. And we'll get more practice with this notation. In interval notation, I'm describing this whole interval, and this goes all the way to negative infinity, and then stops at 2, and we're including it with a bracket. So I would say from negative infinity to positive 2, including 2. And if it goes to negative or positive infinity, the notation is to use an open bracket since it's, or an open parentheses, since it's not an actual value that we can reach. It's not something that we're going to include or exclude. It's more of an idea that it goes on forever. So it makes more sense to use an open um, parentheses. All right, let's look at the second example. We have k is greater than negative 3. So as a graph, let's say we have 0 here, so negative 3 would be over here. And this time we want everything greater than negative 3, so everything to the right, but not including negative 3. It's strictly greater than, so I'm going to make a bracket, or a parentheses, I mean. So in set notation, it'll look similar. We're saying all values, this time it's k, such that k is greater than negative 3. You can kind of just repeat the statement that they give us. And then in interval notation, I would say starting at negative 3 and going off to infinity, positive infinity this time. So those two examples, one including the endpoint and one not including the endpoint. And we're seeing this different notation. So let's look at some inequality statements that we can solve like an equation. So when they list these addition and subtraction properties of an inequality, this is just saying that you can, just like for an equation, you can add or subtract numbers across the inequality sign, just like you can across the equal sign, as long as you do it to both sides. So we can use that same strategy. So let's look at our example 2 here. So we have n minus 9 is greater than or equal to negative 8. And I want to solve this just like we did with equations. I want to get n on its own on one side. With some inequality statement, there's one special case where this might flip, and we'll see that in a second. Um, and then everything else on the other side. So since we have a minus 9 here, you can just add it to both sides. So plus 9 plus 9. And it's just like solving an equation. So we would say n is greater than or equal to, and we have negative 8 plus 9, or 9 minus 8. So this will be positive 1. And it's greater than or equal to positive 1. So it wants us to graph the solution set and to write the answer in interval and set notations. So as a graph, this is 0, so 1 will be here. So everything greater than or equal to. So I will use bracket, and I would fill in everything greater than that. In interval notation, I would say starting at 1, including 1, and going off to positive infinity. And then if I was using set notation, let's say the set of all values n such that n is greater than or equal to positive 1. So the point being here, you can solve these like we're solving an equation. So you can add or subtract numbers across. You can multiply and divide, but there's a special case, which I think we'll see here in a second. Yeah, so multiplication and division properties. It's very similar to equations. This is saying if c is a positive number, then a less than c and a times c less than b times c are equivalent, meaning you can multiply something on both sides of the inequality. And notice it says if c is a negative number, so this is the important one, then a less than c and a times c is greater than b times c are equivalent. The main thing here to notice is that the direction flips if you multiply both sides by a negative number. We can divide on both sides. So we can divide both sides by some number. But then in a similar way, if we divide by a negative, then the direction flips. So that's the main point I would like to, I'll make just a special note here. So if you multiply or divide by a negative number, so if you multiply or divide by a negative number, on both sides, I'll just say, I'll make sure to mention that. So on both sides, you have to flip the direction of the inequality. So it's an easy thing to forget to do, and that can cause you to feel like you have the right answer, but it's not accepting it because the direction hasn't been flipped. But this is only if you multiply or divide by a negative number. That's the main thing. If you do it with the positive number, you don't have to flip the direction. So let's see a couple of examples. So for A, we have negative 6t is less than or equal to 12. So notice if we want to solve this, we have 6 times t, or negative 6 times t. We would want to divide both sides by the negative 6. So we need to flip the inequality. So on the left side, we'll just get t remaining, but instead of being less than or equal to, I'll say is greater than or equal to. And then 12 divided by negative 6 is negative 2. So we had to flip the direction because we divided both sides by a negative. And wants us to graph and write the solution in our two notations. So negative 2 would be over here if this is 0. And I'm greater than or equal to, so I'll use a bracket. And I would fill in everything to the right. So everything greater than or equal to negative 2. Interval notation, I would start at negative 2 using a bracket, and it goes to positive infinity. And then set notation, all values of t such that t is greater than or equal to negative 2. So again, the big point, divided by a negative, so I had to flip the direction of the inequality. And then for b, we have 6 times t is less than or equal to negative 12. The negative is on the other side now. So in order to solve this, notice this time I just divide by positive 6. So even though there is this negative here, what I'm dividing by is a positive number. That's the main thing. Over here we had to divide by a negative. So these 6's would cancel. I would have t is less than or equal to, and then negative 12 divided by 6 is negative 2. So this one keeps the direction. So this time, negative 2 here. This time it's less than or equal to. So I would still include the negative 2, but now I want everything that's less than negative 2. So all possible real numbers less than or equal to negative 2. So as an interval, so the interval is always reading from left to right. So on the left side is negative infinity, and then it goes to negative 2, and we'll include the negative 2. And then as set notation, all values of t such that t is less than or equal to negative 2. You don't always do all three of these notations. I think they're making an extra point just to get everybody used to using them. Sometimes you'll use one and sometimes you'll use the other, kind of depending on the situation. But for now, they're having us practice all these different ways of expressing it. There are just three ways of expressing the same thing, and they're each describing an infinite number of solutions to this inequality. All right, let's look at the next section. So this is just combining some things together. You use a combination of properties. Let's look at the example. they give us looks like what looks like a messy equation. So we have 3 times 1 minus 4a plus 15 is less than 2 times 2a plus 5. So let's just solve this like an equation, and then if we end up having to divide by a negative or multiply by a negative, let's just keep in mind we'll have to flip the direction of the inequality. But otherwise, this is going to feel just like solving an equation. So everything should be pretty similar. So let's start by getting rid of the parentheses. Let's start by distributing this 3 through, and let's distribute also this 2. So this will be 3 minus 12a plus 15 is less than 4a plus 10. And then I see there is some like terms, 3 and 15. So that will become 18. So I could say we have 18 minus 12a. Let's make this a little nicer. 18 minus 12a is less than 4a plus 10. Now, let's see. Well, let's move this 18 over. It's positive on the left side, so I will subtract it from both sides. Minus 18, minus 18. So I'll be left with on the left side, negative 12a is less than 4a, and then 10 minus 18 will be negative 8. Now I will subtract 4a over to the left side. Get all my a's together. Negative 12a minus 4a will be negative 16a, subtracting from a negative. And then this will be less than negative 8. Now here, notice we're going to need to divide both sides by negative 16. So we're dividing by a negative. So we need to flip the inequality. So on the left side, we'll just have a, but instead of less than, it should be greater than. And then on the right side, we have negative divided by negative, so those will cancel. And then 8 goes into 16 two times, and into itself once. So this will all reduce to positive 1/2. So a is greater than 1/2. So it wants a graph, interval, and set notation. So if this is 0 and this is 1, 1/2 would be right in between. And it's just strictly greater than 1/2. So imagine a curved parentheses and everything greater than that. So everything on the right side. In interval notation, this would start at 1/2 but not include 1/2 because it's just strictly greater than. And everything above that, so it would go through infinity. And then set notation, I'd say the set of all values a such that a is greater than 1/2. So again, we're just solving it like an equation. So solving it like a regular equation. So we can use all our rules, distribution, adding and subtracting, combining like terms. The only big change is this flipping the inequality whenever we divide by a negative. That's the main new piece to keep in mind. And then instead of our answer being a single solution, we express it using one of these methods because we're really trying to describe an infinite number of possible solutions. All right. We can also have what are called three-part inequalities. So as you see, like in here, there's inequality symbols on both sides. So this will still be similar, just you'll still want to think about solving this like you're solving an equation, but any operation you do, you need to do it to both sides. So I'll say do each operation to both sides. So I'll show you what I mean by that. So let me rewrite our double inequality. 0 is less than r plus 2, which is also less than 5. So if we just had the right side, I would want to subtract 2 from both sides to move the 2 out. So I'm going to do that same thing, but I'm going to subtract 2 from all of these sides, from everything. So we'll lose it in the middle. I'll just get r. I still have my inequality signs, so you can just drop those down. On the left side, 0 minus 2 is negative 2. And on the right side, 5 minus 2 is positive 3. So what is this describing? It's saying essentially r is between negative 2 and positive 3. You can read it from this direction. R is greater than negative 2, and r is less than 3. Or you could say negative 2 is less than r, which is less than 3. I like to think of it as just r is in between negative 2 and 3, and we're not going to include negative 2 and 3 because there's no or equal to signs here. It's easier maybe to see this in graph form. So this is 0. This would be negative 2, and I'll stick positive 3 over here. And r is greater than negative 2, so I would imagine filling into the right of negative 2. But r is also less than 3, so I would imagine filling into the left of 3. So what we get is this area in between, not including either endpoint. And this time it wanted to answer just an interval notation. So I'll say from negative 2 to positive 3. So yeah, this is an interval. It kind of looks like a coordinate point, but this is an interval of x values, and it gives you your starting point and your ending point. Cool. So let's look at example 6, a bit more complicated. Got some fractions. Let me write it out. You have negative 5 over 6 is less than 1 over 4 times p plus 5 over 12, which is less than or equal to 4 over 3. So we have lots of fractions. We can work with them, but we could also try to clear them out. So we can still use that same strategy of multiplying everything by the least common denominator. So what would be the least common denominator here? Well, I see 3, 12, 4, 6. I know 6 times 2 is 12, 4 times 3 is 12, 12 times 1 is 12, and then 3 times 4 is 12. So I can turn everything into a 12. That's going to be our least common denominator. That would be like the common denominator I would want to produce if I were adding and subtracting these fractions together. So this LCD is 12. So I'm going to multiply everything by 12 to clear the fractions. So let's do that. So I'll go ahead and write it out just to show what we're doing. I'm going to multiply the whole inner part on the right side. Let me just stick everything back in here. This is less than 1/4 p plus 5 over 12 is less than or equal to 12 times 4 over 3. All right. So let's start to reduce as much as we can. So think of each of these as like a 12 over 1, 12 over 1, 12 over 1. So 6 goes into 12 two times. So this will become 2 times negative 5, which is less than. And then here, 4 goes into 12 three times. So there'll be a 3 up top. And then 12 goes into 12 one time. Because I'm imagining this 12 is going to distribute to each of these terms. So it's going to reduce both of those. So this will become 3p plus 5, because it cancels this 12, and then this 4 divides the 12 and becomes this positive 3. And then this is less than or equal to, and then in the same way here, this 3 goes into this 12 4 times. So this becomes 4 times 4. Now let's keep simplifying. 2 times negative 5 is negative 10, which will be less than 3p plus 5, which is less than or equal to 4 times 4, which is 16. Now we're still trying to solve for p, so let's subtract this 5. And remember, we're doing it from all three sides. So on the left side, negative 10 minus 5 will be negative 15, which is less than 3p, which is less than or equal to 16 minus 5, which is positive 11. And then last step here, since we have 3 times p, I'll divide all sides by 3. I'm dividing by a positive, so I won't have to flip the direction at all. 15 divided by 3 is 5, and I have that negative, so it'll stay as negative 5 will be less than just p. And on the right side, we'll kind of have to leave this as 11 thirds. That's like 3 and 2 thirds if we were to convert this to a mixed number, which can be helpful in trying to visualize where this is. Because 3 goes into 11 3 times. 3 times 3 is 9. And then there's 2 left over out of the thirds. 3 and 2 thirds. This will be maybe helpful to produce the graph, because it wants us to graph the solution set and write the answer in interval notation. So let's imagine our number line, and we're greater than negative 5. So if this is 0, 1, 2, 3, 4, 5, we'll go 4 out in that direction. This is negative 5, and let's say this is 4. This would be 3. So p is greater than negative 5, or you could say negative 5 is less than p. When it's at this three-way inequality, I like to read everything from the perspective of the variable. That's why I'm saying p is greater than negative 5, because I'm kind of reading it this way, and p is less than or equal to 11 over 3, or p is in between those two numbers. So greater than negative 5, I have a bracket there, and less than or equal to 11 thirds, which is like 3 and 2 thirds, so maybe something like this. And we will include everything in between. And then in interval notation, it'll look similar. So starting at -5, going to, this time we'll just say 11/3, including 11/3. And that will be our solution. So let's look at 7 now. We have 3 is less than -2m plus 7, which is also less than 13. So let's solve it like an equation. I have a plus 7, so I can subtract 7 from all 3 sides. 3 minus 7 is -4. So -4 is less than -2m, which is less than 13 minus 7, which is +6. And then here I have -2 times m, so I'm going to need to divide all sides by -2. And since we're dividing by a negative, we need to flip the inequality. So on the left side, it's a negative divided by a negative, so it'll become positive, and 4 divided by 2 is 2. And this will be less than m. Oh, no, I need to flip this direction. So 2 will now be greater than m, which will be greater than 6 divided by -2 is -3. So what does this mean? This might be weird to read, but this is saying m is less than 2 and greater than -3. So it's a little bit flipped. So if I'm writing my solution, if I'm graphing it, I would still put the -3 on the left. And we have +2 up here. So m is greater than -3. So I would have a parentheses at -3, and m is less than 2. So it's everything in between. Greater than -3 and less than 2. Sometimes when you solve it, it comes out a little bit backwards like this, especially when you end up having to flip the direction of the inequalities. So that's part of why it's also helpful to read sort of from the perspective of the variable. Less than 2 and greater than -3. And then it wants the solution in interval notation. So I can say from -3, not including -3, to +2. All right, let's see an application. So this says, Keisha is planning a baby shower for her sister. The restaurant charges $450 for the first 25 people, plus $15 for each additional guest. If Keisha can spend at most $700, so that's some total amount, and at most meaning we should spend less than or equal to that amount. That's where the inequality part comes in. Find the greatest number of people who can attend the shower. So we're looking for some number of people in the end. The number of guests, total number of guests. Well, we know that there'll be at least 25 people, and then $15 for each additional guest. So let's let our variable, let x equal just the number of those additional guests. We need to find out how many extra guests we can have. This will be the number of additional guests. And we know that, just to put it in words, the cost of the first 25 people plus the cost of the additional guests needs to be less than or equal to $700. And it says it costs $450 for the first 25 people. So we can just replace this part with 450 plus $15 for each additional guest. And we said X is the number of additional guests. So that would be 15 times X. However many additional guests we have $15 per person then. And then this needs to be less than or equal to 700. Cool. So we got our inequality set up. Let's now solve it like an equation and just watch out for having to flip the direction. So I have this positive 450. Let's subtract it from both sides. So I'll be left with the 15x, which is less than or equal to 700 minus 450. That will be 250. Now I have 15 times x, so I'll divide both sides by 15. I'm dividing by a positive, so I won't have to flip the inequality. So I'll be left with x is less than or equal to, and if you do this in a calculator, let's see, 250 divided by 15, I get 1.6 repeating. So like, or not 1.6, I'm sorry, 16.6 repeating. And so we want to be less than or equal to this. We're going to find out the maximum number. And so we wouldn't want to pick being equal to 16.6 repeating because we're talking in terms of whole people. And even though this is 16.6, we wouldn't round it up to 17 because we can only be less than or equal to this number. So here we would want to round down. From here we would say x will be equal to just 16. So we're rounding down because of the situation of the problem. The problem is talking in terms of people, number of people, and we would only speak in terms of whole numbers. We wouldn't say half or anything like that, or some decimal point. So this is the maximum number of guests that we can have on top of the original 25. So let's give our total number. So total, or they're looking for the greatest number of guests, greatest number of people. So it was our original 25, and we can add 16 and still be under that budget. So 25 plus 16 is 41. 41 is the greatest number of people who can attend the baby shower and not spend more than $700. So total use of the inequality here in this situation. So in general, with all of these, we're really just solving them like an equation, but we had this sort of different way of expressing our solution sets, like graphing it or using interval notation or using set notation. And then the main extra rule was if we have to divide by a negative, then, and this works with multiplying by a negative on both sides too, we have to flip the direction of the inequality. All right, so that was 2.7. We worked with graphing and using set and interval notation. We saw that you can add to both sides and subtract to both sides of an inequality, same with multiplication and division. And we combine those all together. We did three-part inequalities, and then we saw an application question involving linear inequalities. Okay, that's all for this video.